process is looking at methane. So we could look at our Lewis structure for methane, okay, which would be a little more straightforward than what we've got drawn up here. We just have the carbon with our 4 hydrogens around it, which you should be drawing instantly. What we then pushed through in chapter 2 was then looked at this at a Vesper relationship. What is the 3-dimensional representation? And that's where we got into the different shapes of our molecules. And we now have tetrahedrons. We use these wedges and the dashes to represent that 3-dimensional reality. Okay? And that 3-dimensional reality is further kind of drawn in your textbook in a way that's trying to mimic the model kits in that next drawing over. What we've got here is effectively a model kit drawing. What we're attempting to show is the actual 3-dimensional structure. Very hard to do because everything that we do in class is what? 2-dimensional. Okay, so you have to bring these shapes to life. If you got to wear the 3-dimensional or the 3D goggles, go ahead and do that. You need something to get these out of the paper at you. That last representation is kind of a space-filling model, trying to represent kind of a better way to envision that structure. We don't have these long bonds hanging out there. We've got these kind of spherical shapes all kind of overlapping with each other, much like we saw in molecular orbital theory. Okay, we've got the 2s orbital overlapping with our sp3 orbital from our carbon, forming that bond. Okay? So what you should be going through and doing is taking the model kit, even with methane, as simple as it may be, and manipulating it. Turn it one direction, draw what you see. Turn it another direction, draw what you see. Okay? Bring in that art history class that you've learned about and talked about so much in your past, okay, being science majors. Okay? You really need that art skill. Okay? It's all about that perception on what's happening, or perspective. What happens when we move up to ethane? Okay? Well, in ethane, we've got these slightly more complex structures. And again, if we look at our Lewis structure, we've got our carbon with all of those bonds around all of our hydrogens, and we've got our ethane structure. And if we wanted to represent this in 3 dimensions, the drawings just underneath this kind of represent that, except what are they showing in between? Instead of a nice normal bond, what are they showing? They're showing the hybrid orbitals, that overlap. Why is it important to show those hybrid orbitals? What's the next thing they add to this image? They're showing that what happens if we take that orbital overlap with my fingers. What happens if I turn my hand? Does the overlap change? No, it stays constantly overlapped. Which means when we look at the model, that bond can freely rotate. And if we look at our structure from the side and look at those first 2 images, okay, do we really see much of a difference between those 2 drawings? We've still got 2 carbons. Still got 6 hydrogens. Right? 2 hydrogens are wedged, 2 hydrogens are dashed, 2 are solid lines. So yeah, not much of a difference at all. So one of our first assumptions may very well be, well, those are equal energy. Okay, well, is that true? Okay. From lab, you might be saying, no, it's not true. Okay. And what you're remembering in lab is that we don't have to be looking at this molecule from the side, but what can we do? You can turn and look at it end on. Does that change your perspective of the molecule? Absolutely. And that's what those next 2 ball and stick figures are trying to represent. What we're seeing is a different viewpoint. Okay? So let's go back. Let's clean that up a little bit. If we take a look, this hydrogen and this hydrogen, nice and highlighted in red. Both of those hydrogens are in the plane of our board, or the plane of our paper. How do we know that?
Straight line.
We're using just a normal solid line, okay? Not wedges, not dashes. If we now grab one of those carbons, this is a fun little demonstration. I'm going to take the carbon on the right-hand side, and I'm just going to grab it, and I'm going to pull it out of the board, okay? And now kind of rotate it out towards you. Those hydrogens that were now in the plane of the paper are now in the plane coming directly out of the board at you. Okay? And being in that same plane, what we could now go through and do is show those hydrogens. Okay? Oh, that's obvious. Everybody can see that, right? Kind of sarcasm. Really? Everybody can see that? Really? Cannot. Okay. Thank you. I appreciate that. All right. It's not easy to see, so let's envision. Let's see if I can do this with my hands. Stay. All right. My hands are in the plane. What happens if I grab this carbon and pull it out? Now when we look at those hydrogens, where are they? They're both pointed up. They're both in the same plane. Right? So if we're going to draw that, what we're trying to do is show that as best we can, showing that aimed directly up. You'll notice that we've got it slightly off-center. Why would we have it slightly off-center? My fists are the carbons, and I now turn. Can you see my other fist?
No.
Okay, it disappears. So they've drawn it slightly off-center so that we can see that other carbon. Okay? But in this drawing, is that particularly easy to go through and draw? If I asked you all to draw that right now, how many of you could do it? Okay, 2 people? That's not very useful. Okay? So what we want to do is come up with another way to draw this structure, okay, or this relationship, so that we can see it a little bit better. Okay? So what we're doing is taking a look at our eyeball now. It's a good thing I actually had the image here. And we're now looking down that bond. So what I'm asking you to do is now take this carbon on the left. And I want you to pull that out of the board and aim it directly at yourself. Okay? And now we want to draw what we see. Well, probably the first thing we would see would be those hydrogens kind of fanned outwards away from that center carbon. Okay? And that center carbon, would it be bigger or smaller than the one behind it? Bigger. It's getting closer towards you. And that becomes a bit problematic. Why does that become problematic? You can't see the other one. So somebody went through and said, okay, let's spin reverse perspective on this. Let's make that front carbon really, really tiny. Okay? So there's my front carbon, very, very tiny. And we'll call it red all the way through this. Hydrogen A. Where is it with respect to that carbon? It is straight up off of that axis. Remember, we're taking that plane in the board, we're rotating it out exactly 90 degrees, which means hydrogen A is going to be directly straight up from this. What happened to our wedged and our dashed hydrogens? Column B and C. Okay, if we take B, it's aimed at you. If we take that carbon and rotate it out, where is it now aimed? That is your right. Okay. Which would mean right, yeah? What happened to hydrogen C? Well, where was hydrogen C originally aimed? Away from you. And we go ahead and rotate that carbon out. Now where is it aimed? Okay, to your left. And we can now draw on hydrogen C. We can then shift to our back carbon. Okay, this is our reverse perspective issue. We're trying to set this up so that we can see all of these atoms as cleanly as possible. Okay? So in that perspective, I'm going to make that back atom larger than the front atom. Okay? What things are connected to that back atom? We've got a hydrogen. Let's go ahead and call it purple hydrogen A. Where is purple hydrogen A? Directly behind the red hydrogen. Can I draw that easily? Could you draw that easily? No. So what do we do to give a little bit of perspective so that we can see that it's there? We'll just spin it ever so slightly off center. You'll notice that where did I draw that bond? Connected, that line went from where to where? From the purple carbon, which is the circle in back, to the hydrogen. If we take a look at our hydrogen B and our hydrogen C, where's the hydrogen B now? Remember, it's aimed at you, and what did I do? I took that red carbon, I pulled it out of the board. Where's hydrogen B? Purple hydrogen B. Okay, to the side, and it's on the right side. Okay, it's also directly behind red hydrogen B. So what do? offset it by a little bit so that I can pick it up. And hydrogen C, do the same thing, offset it. So you'll notice all those red lines go to a dot in the middle. Why the dot in the middle? The dot is the front carbon. And all our purple lines go to the circle and back because the circle and back is the back carbon. Those lines are very important to be very specific about where you're drawing. If I connected all those purple lines straight up to the red, what am I then saying is happening to that red carbon? It would have all 6 hydrogens attached to it and the purple carbon in back. Okay? So we're trying to offset these things a little bit so we can pick them out. If we go through with the other version, okay, I'll still color code, but I'm not going to walk through it this time. There's our red and our purple. We'll still pull the red out directly in front. We got our hydrogen going directly up, to the left and to the right. We draw our purple carbon in back. And now our purple hydrogen that was in the plane is aimed straight down. Okay. So let's again think back to that original question, something about energies. If we look up at the line angle drawings, we might say, well, those are roughly the exact same. Right? But if we look at our new projection with these weird looking end-on views, can we still say they're the same? Okay? Why are they not the same? So hydrogens are now separated away from each other. Well, why is that important? What does that line represent? Electrons. And if we look at our first structure, which just for the heck of it, let's call it eclipsed. If we look at that first structure, those electrons on that hydrogen and those electrons on the back hydrogen are in the same plane. What do electrons do when they get near each other? They repel. So by locking them in this position, am I going to a naturally higher state or lower energy state? Higher energy. This structure is going to freak out, and those hydrogens are going to snap away from each other. Well, as soon as they snap away from each other, what do we end up shifting into? This other viewpoint. And that other viewpoint we'll refer to as, I think that's right, close enough. And we now have a staggered conformation. Right? And with that, we can now say we have 2 different energy states. Well, if we have 2 different energy states, we need to have these names, which we've classified, and we have to have some way of representing them or looking at the structure. Okay. How important is this particular viewpoint? Well, in the case of ethane, not really a big deal. But what happens if we move up to more complex structures? Right. It starts to become more increasingly important, particularly if we're concerned about energy. So if you see a question that says, which of these 2 structures is higher or lower in energy? What we're actually asking you is to draw these conformations. Draw this view of the molecule. Because once you're in this view, you can now evaluate that energy difference. In the other view, you can kind of pick it up once you're used to dealing with oscillating back and forth between these. But that takes lots of practice. Okay? Look at that, beautiful pictures. So, if we just kind of jump straight up and go straight to butane. If we drew out butane, we got 4 carbons in a straight line. We can look at a couple different line angle things. And we can look at the model, we could again go through our different rotations. And what you'd end up seeing is that we do end up with different energies. Okay? We'll still end up with the similar comparisons that we had with our ethane. Okay, where we've got an eclipsed and a staggered. But you'll notice that when we jump to butane, we're going to end up with 2 variations for each of these. We'll end up with 2 more eclipsed interactions and 2 more staggered interactions. And well, the eclipsed interaction is so high in energy that we don't stress too much about those other interactions. Okay, yes, we can label them, and we'll show that in a second. Okay? But we don't worry about naming those. The ones that become more important is that when we move into the staggered conformation, and you go through those various rotations about that single bond between the two carbons, and these X groups being CH3s in this case, you'll notice that we end up with these, go away, not you, something on my screen changed. Those CH3s. Okay. Would we expect those staggered conformations to be of equal energy? Okay. Why not? They're both staggered. What's the issue with the methyl group? What's different about the methyl group interacting with itself versus hydrogens? What's the difference between carbon and hydrogen?
Carbon has 4 bonds and hydrogen has 1.
How does an atom get bigger? It has more electrons. So as soon as we move from hydrogen to now some different things, those different things will necessarily have more electrons. What are those more electrons going to want? Even more space. Right? So now when we look at these two conformations, in one of those, we expect it to be a little bit higher in energy because the methyl groups have less space. They're actually right next to each other. And in the other case, they're at complete opposite ends. Right? So they have as much space as we could possibly give them without destroying the molecule. Okay? Of course, since we have different names, what does that end up, or sorry, different structures with different energies, what does that mean we need? Different names. So now you have to stack on top of this, not just understanding what the structures are, but the naming behind each of these. Okay? Well, the one where they're really, really far apart, I think, is a little bit easier to name. Okay, they're on opposite sides, hence, whoops, I can spell anti. Anti. And the other one, they're French looking. I don't know. Anybody French? Because it's a neat interaction, right? It's a good thing. Okay, so we have a gauche interaction versus the anti-interaction. So anytime you're now looking at an individual structure, where your bread and butter is going to be is probably being asked between the gauche and the anti-conformations. Okay? How will you know you need to answer a question about gauche or anti? Asks about energy. Doesn't ask anything about energy. Gauche and anti are kind of a meaningless point, or meaningless to look at. So how should you know that you want to draw your structure in this type of projection? Asked for energies, again. Right? And so what you would do is evaluate those structures and compare them between each other. What makes this more challenging? If we ask this question, let's see, can I go back? Yeah, I can. What you would probably see as a question is, which of these two structures is higher in energy? Are either of those drawn in a Newman projection? No. So your first step is to go through and now convert these structures into Newman projections. And you have to decide which Newman projection to pick. Because a Newman projection is just looking down a carbon-carbon bond. All right? So where do we decide? Well, we're trying to maximize the interactions possible. We'll look down the blue highlighted bond there, and we'll look down the blue highlighted bond here. Those of you that have had enough practice with this, which of these two structures is going to result in the anti-conformation? The one on the first, the one on the left. And the other one will be our gauche. Is there a little shortcut we could use by looking at these structures to say? Kind of full symmetry. This bond is aimed upish. This one is aimed downish. Those same direction, opposite direction. Opposite direction. What did anti mean? Huh. On the gauche, same direction or opposite direction? Same direction. There's our gauche. Okay? So you can draw those interpretations from just our standard side view. It requires some practice to manipulate that. Questions? Yeah.
Couldn't you, does it not include like rotating around sigma bonds?
So what you have to realize is that that sigma bond is constantly rotating at all times. So what the question would be is which of these two conformations is lower or higher in energy, regardless. Okay? In that case, what you're asked to do is compare specifically those two structures. Okay? If we change the structure around to something else, then yes, you're going to have to evaluate rotations and look at the lowest energy conformation for each of those. It's a much more advanced question. Okay? Question? Don't be too excited about this. Yeah.
How would we actually draw the Newman projection for like the line? Like where do you put like the other compartments that you're talking about?
Okay. We'll convert one of those across in just a second here. You just brought up another good point that I've been trying to not say, but then forgot to actually say it. These projections, this particular viewpoint, actually shows a difference between structures that we would have thought were equivalent in energy. But now we know they're different in energy. That's a pretty massive conclusion. Such a massive conclusion that what do we end up doing? We give the person credit for discovering it. This type of viewpoint is known as a Newman projection. I've seen a billion different ways, well, probably 2 different ways to spell his name, but Newman is close enough. I think I've also seen it with a U. I haven't spent the time to figure out which one's correct, but Newman, that's what you're looking at. Okay. So back to Madison's question. Let's clear this away. Let's take a look at our drawing here. There's the bond we're going to sight down. We'll call our purple carbon, actually I've been calling the purple carbon the back carbon, huh? So red carbon, there's our front, purple carbon will be our back. So if I'm going to drop my eyeball on this, my eyeball is aimed right here. I'm looking down that bond. Right? Doesn't have to look pretty. So there's my red carbon atom as my front. I've only got one bond shown right away. So let's specify where that one bond is shown, and not the blue bond, the red bond. Where is that red bond with respect to the eye? Straight up. It is technically aimed at the eye a little bit. Okay? But in our Newman projections, we ignore those wedges and dashes. Okay? We just kind of space it out as a flat drawing. So that red bond is aimed straight up in the plane. Are there some other bonds that aren't shown? We've got some hydrogens. So if we drew on those hydrogens, could just draw it like that, but that's a bit meaningless. What do we need to add to those? We got a wedge and we got a dash. Whoops. Let me back away from that for a second. Where are those hydrogens aimed relative to the eye? Above or below? Below. So I need to draw them down below. The apparent bond angle there is 120 degrees. Okay, we got 3 lines bisecting that. What is the real bond angle? 109.5. Okay, it's that weird, you're changing your perspective on the molecule so the angles look weird. Okay, where's our back atom? Sorry, Madison, I see the hand. What's up?
No, I was confused because I didn't think I could do like the CH3, and I feel like stupid for asking.
Don't feel stupid for asking the question. You need a frame of reference.
Yeah, no, I mean, yeah.
I'm still going to finish it. We've got our purple atom in back.
I'm not seeing how the hydrogens are on the bottom.
Okay, so our blue bond, let's see if I can do this. If we look at a perspective, this is an arrow aimed at you, coming out at the plane at you. Okay, just to freak you out a little bit, why not? So our methyl group is aimed straight up. Okay, our hydrogens, oh my gosh, I can't believe I'm doing this. Okay, so if we turn, hydrogen, thumb, hydrogen, pinky, and hydrogen pen. Okay, everybody kind of see, or methyl pen, sorry, methyl pen. Everybody see that in comparison to the drawing up there? Say yes fast. If we now turn, oh, the hydrogen that was coming at you is now on your right side. And remember, the blue bond is my forearm. Okay, where's that hydrogen? Above or below my forearm? Below. Where's the other hydrogen? Where's the other hydrogen? Above or below? It's below. Oh, that's done. So now we've got those hydrogens aligned according to that structure. You see it? A little bit cleaner. A model kit drastically helps for this. Okay? Using your hand is fine. You can do it on the exam. You will find that it is very difficult to do. As simple as that may have looked to you, it's not easy to do. If we go through and look at our back carbon, okay, where's that methyl group relative to our blue bond? Okay, directly underneath it. Why do we know it's not wedged or dashed? Or sorry, left or right of it? Because it's not wedged or dashed. Okay? It's in the plane of the paper. So that when we rotate that out 90 degrees, our paper is now exactly 90 degrees to the board. It's going to be straight vertical, but down. Wow. Where are the hydrogens? Those hydrogens will end up being aimed above. But I'm going to throw in a little corkscrew here just because it's fun to do this. Every once in a while I'll see a student do this. Where are those hydrogens now aimed? Sure looks like they're aimed down. What's the problem with this? You didn't draw the structure according to its three-dimensional relationship. Okay? So this is where drawing the structure as accurately to the three-dimensional model as possible is going to help. And if you build a model, where are you going to see those hydrogens aimed? They will be aimed up. Okay? Following the point of our carbon structure. Okay? So we can now draw in those hydrogens. Man, never doing that again. I probably won't be able to. So, you said it was already obvious, so maybe I shouldn't ask you if you're okay with this. Is everybody else okay with how this came drawn? Get the individual relationships. Can it be made more difficult? Absolutely. How? Throw in wedges and dashes. Put the carbon as a wedge. Okay? Put one of those bonds on as a wedge. Now it's not exactly in the plane. It's going to be one of the side atoms. Okay? It's all about drawing and flipping that structure in a fashion that makes it easiest for you to understand and see. Model kit.
So since the hydrogen ones are going to be ones towards you, do you have to draw the line shorter or longer than the other one?
When you're talking about the purple ones?
Well, no, when we're drawing the Newman, when it's away and towards. Because I remember in lab, I thought like if it was towards you, you had to draw it a little shorter than when it was away from you.
No. So in these drawings, you don't have to worry about the length. And what I'm guessing you're referring to, if I highlight these in blue, are those bonds being shorter or longer than each other? No, there is no preference in that respect. I usually draw the ones in front bigger just because it's easier for me to see, but it doesn't matter. Okay? Other questions? Okay. So, lovely green figure here. We've got various butane structures, all of the individual Newman projections that you could get. And so what ends up happening, if you look really carefully, we've got a green carbon in back. Let's kind of highlight over the top of this. Draw the back carbon highlighted. We got the CH3. There's our loop around to our hydrogens, right? If you move to the next image, that CH3 is where relative to where it started? The exact same location. So to go through and answer a question along these lines, where we're now looking at doing a rotation and how that affects, you'll notice that we've got two carbons that we could rotate, two propellers. How many of those carbons do we rotate? One. Why? It's easier. Do the minimal possible rotations or manipulations as possible. If we now shift to the front carbon, what's happening? we're taking that CH3 and we're rotating it by 60 degrees. We get a new drawing. We rotate it by another 60 degrees. We get a new drawing. Another 60 degrees. New drawing. Okay? And so they looked at all 360 degree, a full 360 degree rotation, and then quantified it with a bunch of numbers. Okay? So let's think about our individual guesses at this. In this first structure, what do we have? Staggered or eclipsed? Eclipsed. Really eclipsed or partially eclipsed? Really eclipsed. The methyl groups are on top of each other. Should that be really high energy or really low energy? High energy. Next one. Staggered or eclipsed? Staggered. Which kind? Gauche. Should that be low energy or high energy? Higher than what? Higher than anti, but lower than our eclipsed. Next one is eclipsed. Really high eclipsed or lower eclipsed? How do you know it's lower eclipsed? Methyl to hydrogen as opposed to methyl to methyl. So we should be higher than our gauche, but not as high as our original eclipsed. The next one is our lowest. Okay, if we now try and connect these, what happens? Ran out of space over there, but we get up there. We end up with an energy curve, which let's say I drew like that. Right? This is accounting for those differences in energies. One of the reasons why we don't evaluate the eclipsed, where is the eclipsed? At a peak. Okay? You're going to love this question. 152. Kinetics, what's at a peak? Activation energy. Does a structure ever exist at a peak? No. That's why we have a transition state. We don't evaluate our eclipsed because the eclipse is ultimately the transition state on moving from one low energy state to another low energy state. It can never really exist because we're at a peak. Okay? So we could now go through and quantify all of these energy differences. If I gave you a bunch of numbers, you could go through and rank and put all this fun stuff in there. Okay? I don't like numbers. Goody for you. Okay? What I do expect you to do is exactly what I just drew out. Okay? This is higher, this is lower. This is higher, oh, this is a little bit lower. This is a little bit higher, a little bit lower. Okay? You should be able to see those differences. Okay? So let's see some hands. How many of you see those differences? Wow. Okay. I'm talking too slow. Cycloalkanes. Within our cycloalkanes, we see a little bit of material show up in chapter 4, and a lot of it show up in the nomenclature chapter. Okay? I don't really like talking about them too much because a lot of the things that we would expect to see within standard single bond structures don't exist. For instance, what type of bonds do we have between each of our ring carbons? Sigma bonds. And what can a single sigma bond do? Freely rotate. Can any of these structures rotate freely? No, why not? The ring prevents it. Okay? Without a model kit, you could try and do it with your hand. Okay? Take your index finger and rotate it the other direction. But don't break your hand. Okay? You're not going to be able to do that without breaking something. Okay? It's not going to happen. Your rings prevent rotation. Okay? What other type of bond prevented rotation? Pi bond. When do you see a single pi bond show up? Okay? Careful. We don't see it for triple bonds. We will see it for a double bond. When you have a sigma bond, a single bond, and the double bond, being the extra bond, our pi bond. Okay? So we have two bonds connecting our carbons. If we go through and take a look at the cyclopropane, I have two bonds connected to carbons of my ring. What's a double bond? A double bond is a two-membered ring. It's the exact same thing. It's a cycloalkane, okay, with only two carbons. Okay, so it has the fundamental concepts of the rings. So what happened with a double bond? You can't rotate. So what happens when you move into a normal ring? Can't rotate. Okay? The ring, just like the pi bond, prevents that rotation. If we go through and look at hybridizations, what's the hybridization for every single carbon shown so far in this drawing as soon as I quickly erase the double bond? sp3 hybridized. What bond angle would we expect? 109.5. What's the bond angle in an equilateral triangle? Not 109.5. How about the bond angle in a square? 90 degrees. Not 109.5 degrees. Is that going to change some energy dynamics of these?
Yes.
Yeah. So what ends up happening is as we now add carbons into our ring structure, we actually relieve stress on the molecule. Because what happens to the bond angle as we move further up by adding carbons? The bond angle gets broader and broader until we hit the 109.5 degrees. That optimal shape happens with our cyclohexane, which is a bit odd because what's the bond angle in cyclohexane? Or, sorry, let's try that again. Not cyclohexane, and hexagon. It's not 109.5. Why? Because in a cyclohexane, what ends up happening? Does it stay flat like a hexagon? No, it puckers. That puckering action is happening in each of these individual structures. And depending on what we wanted to look at, we could evaluate each of those puckering actions. How are we going to evaluate that energy? What do you look at when you need to look for energy? Newman projections. So you could go through and draw a Newman projection for every single one of these and see what the structure does to get out of that high energy state. What you'll find for the cyclopropane and cyclobutanes is that both of those are almost perfectly eclipsed. But there's a little bit of wiggle, and that butane pops it out just enough that it's not perfectly eclipsed, it's twisted. Do you really care that it's twisted? Probably not, but there's a whole section on the chapter on it. Okay? So that's kind of what's happening within our ring structures. So you see this increased term of bond angles and torsional strains and rotational strains and all of these other strain terms. I do expect you to read over it. It's not important to the overall understanding of what's happening within the structures. Think about the pictures, think about the images and their three-dimensional shapes. If you can't label or tell me on an exam specifically what type of strain it is, but you can explain the strain, you got it. Okay? Big part of chapter 4, in fact I think it actually starts with it, is this fun little diagram because what we're now evaluating is differences between structures. Okay, we've already started to piece some of these out. Okay, the top two are a fun one, okay, which you can see better on that far screen. What's the relationship between these now red highlighted structures? So some people might look at it and say, well, those are different because they look different. Okay? The way that I would look at it is, what's my name? What's my name now? It's still the same, right? All I did was just move, take advantage of my space and what I can individually do, and yet my name does not change. Same thing's happening up here. What type of bonds connect each of those carbons? Sigma bonds. And what can sigma bonds do when not locked in a ring? Freely rotate. And what's happened in this case is that we've just rotated about that sigma bond. Okay? That rotation doesn't change the molecule, it changes our perspective of the molecule. Okay? It's like looking at a Newman projection. It's still the same molecule, but we now have a different perspective of it. Which means when we go through to try and determine the relationship between those two molecules, we have to be very careful in how we go through and define that relationship. So chapter 4 takes you through pretty much this table and evaluating the differences between them. So if we looked at our molecular formulas for these, both of them have 4 carbons. Both of them have 10 hydrogens. 10 hydrogens, yes. Right? So they have the same molecular formula. So we can move to the yes branch of our flowchart. We still have structure A and B. So now we ask a new question. Are they superimposable? I'm pretty sure we talked about superimposable in class, right? Yeah. We're overlapping our structures so they completely mesh. Well, in the first case, they don't completely overlap. But what can I do? Sigma bond rotation. Now do they overlap? Yes. That classifies me under the yes branch, and the relationship between those two structures is that they are identical. How about the next two structures? Okay, ooh, good, two good solid answers out of that. Isomers and structural isomers. Okay. Same molecular formula. Are they superimposable? No. So they aren't identical, but that puts us into this isomers category. So now the question that pops up is the same atom connectivity. Okay. That can be a bit of an odd statement to make. So the example I like to use is this one, actually. Let's go through and number these carbons, or sorry, name these carbons. And you should be picking numbers as names. This first carbon should be named 1. Next one. 5. We do the same thing with the other structure. What do we get? Where's carbon 5 connected in our first structure? To carbon 2. Where is it connected in the second structure? Carbon 4. Have we changed the atom connectivity? Yes. We changed the location or the numerical value of where our atoms are located. That puts us into structural isomers because we have a different atom connectivity. Okay. The other category is stereoisomers, which subcategorizes out into at least 2 categories depending on how you want to define it, but that's chapter 5, and that's for Wednesday. Cliffhanger. So, what is the relationship between these structures? Oh, that was a pretty big typo. Why did you say they were different? They don't have the same formula because this one down here has that extra carbon. So let's bust out the fancy eraser. Now what's the relationship between these structures? It's going to take a little bit. I know that flowchart was really helpful, and I just removed the flowchart from your interpretation abilities. You all wrote that down, right? So, did they have the same molecular formula? Yes. Were they superimposable? Okay, I'm hearing some yeses and nos. Let's take a closer look. You may not be able to see that, but that's a dashed that I'm going to just do right through that CH2. Okay. So if we overlay the rings, do the rings overlay? Yes. The top methyl group? Bottom methyl group? No. There is nothing I can do to that ring structure to get those bottom methyl groups to overlap. Okay? Or if I do get them to overlap, what ends up happening? The other one then doesn't superimpose. Okay? So they are non-superimposable. Do they have the same atom connectivity? Okay? So when we go back through, if we went through and did all the numbering, we would encounter that, yes, they do have the same atom connectivity. Okay? Which means the relationship is stereoisomers. It's not even though one is away and one is towards. It is because one is away and one is towards that they are stereoisomers. Okay? What stereo is referring to, for those of you that may be remembering from the handout, is that your atoms are arranged differently in space. Okay? Before it was numerical. Okay? We changed their numerical alignment. If we go through and take a look at these, how are they arranged differently in space? Well, if we just directly overlay on top, okay? This methyl group is aimed where in space? At you. Where's the other one aimed? At you. This methyl group here, being dashed means it is aimed away. Where's the one above aimed? Towards you. Are those aimed in the same direction? No. They are arranged differently in space. Dun, dun, dun. Okay. Not a lot of better explanations than that, other than trying to build the model and superimpose those and see that those methyl groups are aimed opposite directions. And there's nothing you can do to get them to aim all the same direction. Okay? This gives us an issue with cis and trans. We saw this before. When did we see cis and trans show up before? Where did cis and trans show up? Chapter, you didn't have to give me a chapter. I was referring to the concept, but that works. Double bonds. We had cis and trans issues pop up with double bonds. Okay, which, you're right, was chapter 3. Good job. So cis meant that they were on the same side, all those similar sounds. And trans meant they were on opposite sides because they didn't have the same sounds. Right? Oh, that actually kind of makes sense. They don't have the same sounds, they go opposite directions. Okay? Fine, I thought it made sense. Right? So that's our cis and trans. Those popped up with double bonds. Well, what did we say was similar between rings and double bonds? A double bond is really just a two-membered ring. So if I have cis and trans with two-membered rings, what's going to happen when I have 3, 4, 5, or 6-membered rings? I'm also going to have cis and trans. So I can now look at those two structures and I can add some more information to it. In structure number 1, which I'm about to write, what is the relationship between those methyl groups?
Cis.
How do you know they are cis?
Same size.
They're added both coming up. And the other one, they are on opposite sides, so they are trans. We're using the same nomenclature system that we already did, which is technically not a nomenclature system, but we'll cross that bridge in a second. Okay, questions? Oh, yes.
Well, when we did that, we would basically, like one of the rules which you would break, you would just draw a line through the double bond. How do you know where to like draw that line?
Sorry, excuse me. So, with the double bond, you could split the double bond. You don't have a double bond to split here. What you're going to do instead is look at the plane of the ring. Where is the plane of the ring in this cyclohexane right now, as it's drawn? It's the plane of the paper. Okay? Where is this methyl group aimed? At you, or away from the plane of the paper towards you. Where's the other one aimed? Away from you. Okay, so they're on opposite sides. So your frame of reference is now the plane of the ring. Okay, even if the ring isn't planar like it is here. What's that?
So if we only look at the two, say the methyl and methyl, can we have more groups attached to the ring, and how are we going to do that?
Good question. What happens if I now draw this? Okay, for that top structure. And let's do the exact same thing on the bottom structure. In the top structure, what's the relationship between your methyl groups?
They're all equal.
Okay. Here, everybody say all on the same side. So same side, cis. Reasonable conclusion, right? How about the bottom one? Two of them are cis, and the other one's trans. Cis and trans only gives you information about two groups. As soon as you add a third, cis and trans is meaningless, technically. We can kind of cheat on that first one and call that one cis. It's not correct to call that structure cis anymore. Okay? You need a new nomenclature system. Okay? That new nomenclature system, just since you asked, we'll preview it. For cis, Z. For trans, E. What makes this even more fun? Z and E only work for double bonds. Now that we've got these rings, how do we figure out what happens with our rings? Guess what? You now have to go through, and at each of those positions that you have that methyl that is now questionably up or down, you have to label its orientation. That orientation in space is referred to as our R, or our Kahn-Ingold Prelog rules, chapter nomenclature 4, 3. It's the chapter right after chapter 5. Okay, in our sequence. It's not chapter 6 because it's nomenclature technically. You'd have to assign each of those positions a signifier as R or S. Okay. With double bonds, you'll shift to the Z and E, and that is your official nomenclature rule. Cis and trans is a relative location of any two groups. So they could be hydrogens, they can be anything you want. To name specifically, Z and E, or this other Kahn-Ingold pre-log rule system, which is R and S.
Can you not worry about RMS right now? Just
For the moment, no, you don't need to worry about it. But by Wednesday, yeah, you need to worry about it. Okay. Cyclopentanes and cyclohexanes. As we add more carbons into our ring structure, we can start to see that our carbon atoms can move a little bit more. You try and move a carbon atom in a cyclopropane, we're even able to build the cyclopropane to begin with your model kit. You try and move one of the carbons and only one carbon, you probably just broke your model kit. Okay. With the cyclobutanes, if you're lucky, you can get it built and you'll get a little bit of wiggle there, but more than likely you'll probably break your model kit then as well. Cyclopentane and cyclohexane, when you go through and build those, you will notice that there is a significant amount of wobble or wiggle in those. Okay? And what we end up then doing is looking at those possible conformations or those possible wiggle motions and seeing what the structure looks like. When we look at the cyclopentane, its lowest energy conformation obtains something often referred to as, let's see if I can draw this nicely, an envelope. I know it doesn't look nice, but that's what it is. This is the flap. Okay, there's the stickum. And you then fold that down over the envelope. Okay, so you end up with the envelope conformation for a cyclopentane. You'll also notice that in this drawing, do you see any wedges or dashes? No. Are wedges and dashes implied in this? Yes. We're now drawing in 3 dimensions without specifying wedges and dashes. Nasty, but that's the way it works. Right? With the cyclohexane, you'll notice that there are a variety of different orientations that you can flip through, but there will be 2 very common ones. And if you're really lucky in the process of putting it together, it will actually snap itself into a particular conformation. Those conformations are more commonly referred to as the chairs. Those chairs can face opposite directions. So if I sit down in the chair on the left, my head is here, my little smiley face, a creepy smiley face, and I'm staring off to the left. Okay? There's my head down to my back, there's my butt, and there's my legs hanging off the end of my little chair. Saying hi to everybody, not flipping you off. That's an open hand. The other chair, there's my little smiley face head, and I'm not going to go through and draw the body again. Aim the opposite direction. As you may already notice, by looking at those chairs, as I've got them drawn, you will find that you can draw one better than the other. You just kind of have to deal with it. Okay? You are expected to be able to draw these. It will show up on the test that you need to draw proper chair conformations. Okay? To pick up that practice, you need to just practice it and do it. There are some rules that I have found that help. It turns out that my rules are the same as the textbook, which I thought was kind of cool. Independent discoveries. I didn't read the textbook and go, oh, I got it. Okay, start with your seat. Okay, we're going to take 2 staggered parallel lines. And if you rewind the video back and look at how I drew the other ones, you'll see I'm doing the same thing. So I'm taking 2 lines that are roughly parallel and I'm staggering them. I want roughly the same length. Now we can pick the left or the right side of this molecule. So what I'm saying is I'm cutting this in half. Okay, now if I look to the right side, I'm going to take the short line, okay, and I'm going to draw up or down, depending on which side it was. So what's the short side on the right-hand side of this structure? Top or bottom? Bottom. So from that point, I'm going to draw down. Okay? I'm not going to draw straight down, but I'm going to kind of angle around a little off to the side. Okay? And I'll go through and draw that other line on the other side. The other side, the short one, is on top. I'm going to go up a little bit. You'll notice that those 2 red lines are roughly parallel. Okay? Just like the 2 black lines are roughly parallel. One of those words. We can now complete the triangle by drawing in our orange lines. And we now have a chair facing which direction? To the right. Okay? This whole which direction is the chair facing is an exceptionally challenging question because I see the chair aimed directly backwards. Anybody see that chair? Yeah, not particularly easy to pick up. There are chairs all over the place within individual model kits. You have to be looking at the proper conformation to be able to pick up where your chairs are. Okay? This would be our feet. This would be our back or our head. That is the standard viewpoint of our chair. This line is coming out of the plane at you. This line is almost always just shown solid all the way across. That's because it's already out of the plane at you. It's not coming out any further. And then this other one coming out of the plane to catch up with it. Okay, so those bottom, what is that, 3 lines are all coming out of the plane. The other 3 are behind the plane. The only 2 atoms that are actually in the plane of the paper would be where you put your head and where you put your feet.
So when you see a chair drawn without the wedges and dashes,
This is implied.
Okay.
This is implied. Okay? If you want to switch the chair the other direction, you'll notice that I drew my first 2 seats. My chair was sloped upwards towards the right. If I want the chair to face the other direction, I'm going to draw the same 2 parallel lines, but I'm going to have them sloped upwards to the left. I'm also going to shift the stagger off. Okay? Takes some practice. You do need to pick it up. So, of course, we get the next fun question. What do you think we're going to have to do if we're going to ask this question? We need to look at energy. Based on what we've talked about, what do we need to look at energy? Newman projections. Well, we looked at butane as a Newman projection, and that was complicated enough. If we're now going to look to chairs for Newman projections, same deal. You're going to take 2 Newman projections, and those 2 Newman projections will be fused to each other. This will give us information about our energies. So if we take a look at the drawing on the left, we've got our standard Newman projection, our standard chair, and we're looking down those 2 eyeballs. That gives us the Newman projection shown on the right. Okay? Yeah, everybody that hasn't picked up a model kit, this is obvious to you, right? Okay? It's usually brutally difficult. Okay? It takes time and practice to be able to see this. The big conclusion that comes out of this, however, is what happens. Now I forget what my next sequence of slide is. What happens with our different atoms or our different locations? So we take a look at hydrogen here versus a hydrogen on that exact same carbon here. Would we expect those to be the same energy? This is a really hard question, believe it or not. Let's add another tier to this. It is now frozen and locked in place. So we cannot do any ring flips, bond rotations, any of that. Are those red and blue, or the red and blue hydrogens, the same energy or different energies? Different energies. All right, how do we know that? What we'll then do is look to our Newman projections, and what we're concerned about is what does those red and blue hydrogens project to on the back carbon. So we look at our back carbon, and we have 2 hydrogens, and we have a CH2 from our ring. The back hydrogens I can't do anything about. Okay? And ultimately, they're going to see the same kind of hydrogen interaction all the way through. The one characteristic that stands out as big and different is this carbon. That carbon has more electron density, which means what? I want to get groups as far away from it as possible. I only said I can't rotate these. So which of those 2 hydrogens, red or blue, is higher in energy? The red, because it's closer to the big honking group of electrons. What type of interaction is there between the red and the purple? That is now a gauche interaction. Between our blue and our purple, that is an anti-conformation. Okay, because our chair is identical, hydrogens all the way around, we can flip and rotate and do this as many times as we want. Okay? The energy to do a chair flip is really, really low at thermal temperatures, it'll do it on its own. So the hydrogens are officially of equal energy because the chair is constantly flipping back and forth between its two states. Okay? Which means at one point, the red hydrogen is close to the methyl, and at another point, the blue hydrogen is close to the methyl, okay, or our CH2. But what happens if we change our structure around? And instead of having, say, all hydrogens, we put on a methyl group, a CH3. Well, now our interactions aren't all exactly the same. They have a slight difference. Which of those two positions is lower in energy? My blue methyl, or A, or my red methyl, or E? E is lower in energy because if I look at its Newman projection, we're projecting to that carbon. And that is an anti-conformation. Whereas if we look at the blue, it's a gauche. Okay? So what we end up concluding from this information is that I want to put my largest groups, whatever those groups may be in a ring structure, in the E position. What is the E position? Equatorial versus axial. That's it. That's the big conclusion of all the Newman projections and drawing stuff. Put your big group equatorial. 99% of the time, you're right. 1% of the time, you have to look at it a lot further than that, and that 1% you will probably not see in this class. But if you move into a more advanced organic class, they might throw it at you just to be mean and nasty. Okay? That was a stupid statement right there, wasn't it? Lowest energy groups placed the largest in the equatorial. That's a pretty big typo. So if you happen to fall asleep, now's a good time to wake up. Okay? Questions?
How do you do it with the bottom CH and not the top? Or not the one that's on the front?
Good question. These two, what's the bond angle between those two? 109.5. What happens if I do a chair flip? Why is it still 109.5? They're connected to the exact same carbon. That bond angle will never change. What you're looking at is your Newman projection to the carbon in back that's not attached to the same carbon. That's where you'll see a difference. Okay? I'm pretty sure, well, I know we're done. But I think all we've got really now is some kind of just talk stuff at the end. Yeah. So we got 3 slides. We'll start off Wednesday looking at some examples. So I'll want you to go through. We'll work through all of these, maybe 2 or 3 of these. You should go through and do them on your own, so when you come in for class, you can ask questions about how to draw them if you didn't get it right. Okay? We'll then talk about one more way to look at structures, which is your Hayworth projection, and then we are done with chapter 4. These are the sections that you need to review on your own. Okay, I provided an extra formula here for you. You can go ahead and use that. We will talk about that formula again as well.